Today I'm going to be discussing the reasons why some organic reactions just happen and some do not, even though on paper they look eminently plausible. But before we get going, if you would like the notes that accompany this video, there's a link in the blurb to the Crunch Chemistry website where you can find them and lots of other really useful stuff to help you get through A-level. Consider these two reactions. In the first one, the reaction is between an acyl chloride and hydroxide ions. In the second reaction, we have a reaction between a carboxylic acid and chloride ions. You'll notice that to all intents and purposes, reaction 2 is the exact opposite of reaction 1. The reaction mechanism for the first reaction is well known. So we have a delta positive carbon atom because it's bonded both to the oxygen and the chlorine, and they're both considerably more electronegative than carbon. So hydroxide ions attack the central carbon atom and use the lone pair of electrons to make a bond between themselves and the carbon. And this causes the double bond to break. We end up with an intermediate. So we've got a change in geometry. And the carbon is now bonded to 4 groups. At this point, the double bond reinserts itself and the carbon chloride or carbon chlorine bond breaks, and the chlorine leaves as a chloride ion, taking the electrons with it. We can imagine exactly the same reaction mechanism for the second reaction. We've still got a delta positive carbon. In this case, it's bonded to 2 oxygens. And there's no reason to assume that the same thing wouldn't happen. Chloride ions would attack the carbon. Electrons from the double bond would move on to the oxygen. In the intermediate second step, double bond is returned and the carbon oxygen or the carbon hydroxide bond breaks, and we end up with our products. However, the first reaction happens. The second reaction does not. Let's see if we can figure out why. This is the energy profile diagram for reaction 1. The first thing to note is that the products are of lower energy than the reactants, i.e. the relative energies of the acyl chloride and the hydroxide ion are higher than that of the carboxylic acid and the chloride ion. In the first step, the step with the greater activation energy, we've got the bond forming between the oxygen and the hydroxide ion and the delta positive carbon. And we have our intermediate. And in the second step of the reaction, the intermediate goes on to react to form the products by breaking the carbon-chlorine bond. And this step, as we can see here, has got a lower activation energy. If we think about the second reaction, where we have got a reaction, theoretically, between carboxylic acid and chloride ions forming a bond with the carbon, double bond to the oxygen breaking, we end up with exactly the same intermediate. Now, this intermediate, at this point in the reaction, we've got 2 choices. We can break the carbon-oxygen bond, and the strength of a carbon-oxygen bond is around about 450 kilojoules per mole, or we can break the carbon-chlorine bond, and the strength of a carbon-chlorine bond is around about 350 kilojoules per mole. It's far more likely that the weaker carbon-chlorine bond is going to break, in which case the reaction ends up back where it started. The intermediate reverts back to the starting materials, which in this case are the carboxylic acid and the chloride ions. The second reaction doesn't go anywhere. Now, in terms of fancy speak, what we often say is that chloride ions make good leaving groups. Hydroxide ions do not. So let's look at that in a little bit more detail. So what makes a good leaving group? Well, there are two key factors. One, the strength of the bond between the leaving group and the atom it's bonded to. And two, the stability of the leaving group once it's left. We've just seen the first factor at play. Chloride ions make better leaving groups than hydroxide ions because this carbon-chlorine bond is weaker than a carbon-oxygen bond. So given the choice, the weaker bond is going to break. Remember that in each of these examples, R stands for an alkyl group. So we're talking the rest of the molecule. It could be a methyl, ethyl, it could be something far more complicated. Similarly, if we compare halide ions as leaving groups, we see that iodide ions are better leaving groups than bromide, bromide than chloride, chloride are better than fluoride. And that is all down to the strength of the carbon-halide bond. A carbon-iodine bond is the weakest, and the carbon-fluorine bond is the strongest. In each of these cases, once the leaving group is left, all the halide ions are relatively stable. So strength of bond is key here. Fluorine, oxygen, nitrogen and carbon are all in the same period of the periodic table. What makes the fluoride ion a better leaving group than the others is simply that the effective nuclear charge felt by the outer shell electrons in fluorine is stronger. It pulls its electrons in more closely because it has more protons in its nucleus. This means that the fluoride ion is of lower energy and more stable than the hydroxide ion. The CH3- here is our least stable ion, so it makes a very poor leaving group. Water is a better leaving group than hydroxide ions, simply because it's leaving as a neutral molecule. Similarly, N2 nitrogen makes an excellent leaving group. It leaves as a very stable neutral molecule. The triple bond inside a nitrogen molecule is exceptionally strong, so the likelihood of N2 adding back into the molecule it's just left is pretty unlikely. In addition, nitrogen and water make good leaving groups because when they're bonded to the alkyl groups, the rest of the molecule, they're positively charged. This means that they are pulling electron density away from the rest of the molecule to try and stabilize that positive charge. As a result, these bonds are weaker than one might expect. So not only are our leaving groups leaving as neutral molecules, which makes them stable, the bond between them and the rest of the molecule is weak, which makes it more likely to break. Indeed, one of the ways that we can turn a hydroxide ion into a better leaving group is to protonate it, so that, for example, under acidic conditions, the oxygen would use its lone pair to make a dative covalent bond to a hydrogen ion, and then we have indeed got our considerably better leaving group. For example, in the reaction between alcohols and hydrogen halides. If this has been useful to you, then please hit the like button, subscribe and share. It makes a huge difference to a small channel like us. I look forward to seeing you next time.